We're gonna go like this.
All right, we're live. How's it going, guys?
Good.
How's your day been? That's good. So my name is Kyle Dampier. Today I'm going to be doing an introduction to machine learning. If you guys have any questions, feel free to stop me. I'm going to be going pretty quick. A lot of this stuff's pretty high level, but I hope you guys like it. So we already talked about this at the GBM, but I'll go over it again just in case you weren't there. What are ML Mondays? We basically just want to, they're basically just machine learning lectures that typically follow this general guideline of why, how, and what. For the why, we try and focus on why a particular solution was made for a certain problem, and the why just describes the problem, like what problem we're trying to solve, whether it be what type of inputs and what type of outputs we want to produce. The how is basically just like high level math, or like the sort of understanding of what's happening with these models. And the what is what you guys can do to sort of implement these things, like current modern libraries that have already optimized the code for all this type of stuff. This is the schedule. So today we have Introduction to Machine Learning. This is just like to get you guys thinking about machine learning, types of projects you can do, and just teach you guys what exactly a neural network is and how and why it's so powerful. Week 2 is the deploying machine learning models using Docker. We're going to collaborate with ACM. They're going to be teaching Docker, and we're going to be teaching how to make an API for your machine learning model. That's a couple weeks from now. That's 2 Mondays from now. Week 3 is still to be determined, but I talked with Patrick, and we're going to change it to transformers or diffusion models because that's more applicable to the teams. And we're going to talk very high level on that as well. And then after that, we have week 4, which is neural networks from scratch with DSI. Matthew back there is going to be with us teaching that. Week 5, we have auto-regressive integrated moving averages. I just like to say ARIMA. That's a Wednesday. That's also with Matthew. That's with DSI. And then week 6 is going to be genetic algorithms. We're going to collaborate with the Video Game Association, and we're basically going to make a genetic algorithm that plays a game, which I think is going to be one of the cooler ones that we've done so far. That's with DSI. This one's with the now known as Develop. Okay, so the agenda for today. So first we're going to be talking about what are neural networks. Then we're going to be talking about types of applications for these neural networks, which we're going to bring in Monsi and Gabe to talk about a couple of examples. And then we're going to do a sort of quick intro to Tensorflow. So let's start with what are neural networks. So you guys have probably seen this picture before. You were going on the web, you were like, what is machine learning? And then this thing pops up like 20 times. But it doesn't really say anything. It doesn't really mean, like, it's just like a bunch of circles and lines. Have you guys seen this before? No? Yes? Some people? Maybe? Yes, no? So essentially, we are going to break this down and tell you exactly what these components are. First, we need to define the inputs and the outputs. So normally, when you're thinking of an equation in math, you think f of x equals y. Like there's some input, it gets transformed into an output y. That's the same thing with machine learning. We define our inputs. Normally it's a list of inputs, and typically you want them to be as independent of variables as possible, which means like if x and y, say one is x and one is x squared, you want them to be 2 completely separate variables. You don't want them to be connected. F of x equals y. So in this equation, we have f of x equals y, and then the inputs, so the f of the inputs is equal to the output. So that's the basic idea of what a neural network is we're trying to fit some function f. Oh yeah, and then Since we're doing stuff on types of images today, they can be broken down into lists of numbers, which are just each pixel is defined in its own array and flattened. So after that, we have weights and biases. So the lines of this sort of diagram are the weights. Those get multiplied. This scales the function. This moves the function. This makes the function either go up or down. It adds, like, it kind of scales these sort of input, so it creates the preferred output. And it looks something like this, where we have our weights f of w times x equals y. The red circle, each node has its own bias, and the bias is the same for all the weights. It just adds on at the end. It's like when you do an integral. Who here's taking calculus? Okay, we have enough people who've taken calculus. It's essentially after you find an integral, it's the plus c. That's the main idea, where you're shifting the function to go exactly where you want it to go. And so now we have this function w of x plus b, so the weight times x plus the constant that you're trying to find is equal to the output. So you're scaling the inputs to create an output. So if say we wanted to change the shape of a function, we would change the activation function. So this tries to fit the inputs to a certain type of function. And so, for example, so this is the type of f. So we could do things like lines, we could do things like parabolas, logs. We can do things like a sort of exponential function, arctan. Pretty much anything you can think of, as long as it's differentiable, a machine learning model can fit to that sort of a regression line. So what are the different types of activation functions? That'll come up shortly, right after I go over the big picture here. So essentially, if we add all these together, they all have their own weights, they all have their own biases. You can see how we could fit a number of these sort of independent variables to get whatever output we want to expect, right? And so basically, that's all a machine learning model is it's just a way to solve for the constants of these types of equations. So like in a log where there's like a weights and a bias, it's just a way to solve for the constants inside of sort of within a function. So here we have the f of x is equal to the weight times x, and then the entirety of this is the bias plus all the inputs multiplied by whatever weights we find. Okay, so let's talk about activation functions. They're really just a regression model where you try and each iteration you go through, each new set of data that the model sees, you try and find a new regression, and you basically try and find these regressions for each different set, and then you slowly change it over time to fit the average of whatever your model is trying to fit. So the most common one now is a rectified linear unit, where it's just the max of some values, some constant c, and the weight times whatever thing is there. So it shifts it up and down and can move in throughout the graph. This is really, and then another one is TANH, arctan. This one's often used for finding things like whether or not to keep things. So there's a model called long short-term memory, or LSTM. This is used for the forget gate, for whether or not you want to keep or forget past data within the network. And sigmoid is very often used as a softmax function. I'm sure, have you guys heard of that? Softmax? No? Okay. But essentially, if you have classes, this is really good for predicting the probability, because the sigmoid is essentially like, it's almost like, I don't know how to explain it. It's really good for like modeling a sort of a probability of something being within two classes. And then there's a bunch more. Like there's a new one that came out that's like an activation function that tries to fit to distributions and stuff like that. I forget what it's called, but like a normal distribution or something like that. So what happens when you change the weights of things? So the function we're using here is a sigmoid. So sigmoid x equals y. If we change the weight w to be less than 1, you can see it becomes a little less steep, but if we go higher than 1, it becomes more steep. That means normally if the weight goes higher, it's more confident that it's going to be in that sort of area where it's going to switch over to, like, say, another class or something like that. Does that make sense? Okay. And then input, so the input x, I don't know why I put that there. And then, yeah, the weights move it left and right. So changing the biases, it basically does the same thing, where it takes this sigmoid, weight w, input x, bias b, and it shifts the function left or right based off of where it needs to fit in order to classify these different types of functions. So are there any questions? Nope, all right. So how do we learn the weights? Back propagation. That's a big term. I'm gonna go. If you guys have questions, let me know. It's gonna be very high level how I'm gonna talk about this. And I also want to point out that back propagation is only one method, and there's many other methods for trying to find the weights and biases of a neural network. So here are the general. So here's a graph for those of you who have never seen a loss graph before. This basically, these are the two independent variables, x1 and x2, and this plane right here is the loss function. So the first thing we need to do is define the loss function, which in this case, in this graph, becomes the plane. It's where it's like the actual value of the loss function is the plane. And the idea is that the loss is the actual minus the predicted. And the predicted in this case would be like your activation function with the weights and biases already in it. So like you can figure out what the sort of derivative is from your like sort of activation function, right? So then in order to say go from epoch 1 to epoch 2, you would essentially calculate the derivative at the point that you're currently at and find the direction and the magnitude and direction of where your sort of inputs need to go in order to make the loss as low as possible. Does that make sense? So you're basically going to a point, you're finding how you need to shift your sort of inputs based off of like how this sort of independent variable shifts when you change. So it's like dx1 d loss, for example. So it's like the derivative of x1 based on the derivative of loss, how if we move it a certain direction, yes.
So you want to change the weights and biases to minimize this loss function?
Yes.
Okay.
So what you're basically doing is finding the local minima and maxima of your loss function, right? So you're basically optimizing your loss function is what like back propagation is. And then in order to make it so you have more of an idea of the rest of your data set, you define something called a learning rate. The learning rate basically tells you how fast you want the point to move after sort of each iteration. Because say if this goes here and then it finds like a really deep hole, but it moves a lot, it can move around to like random sort of losses if you have a really high learning rate. But if you have a really low learning rate, it'll take a lot of iterations to find the local minima where you want to actually be. So basic idea is you want to try and, I guess, find a happy medium. Third, you actually go through and you change the weights and biases, changed off sort of based off of where the change of your sort of inputs need to go in order to find the local minima and maxima of your loss function. And then you repeat until you get like a decent loss function or you find a local minima. And so, oh yeah, are there any questions before we go on? Yes?
So is the learning rate like your step rate between each epoch?
It's basically like, it's like the weight of, so every time you go through each sort of epoch, it's how much the inputs, how much you want the weights and biases to actually move when compared to like how, so like it'll be scaled based off of like what the derivative is and how much it needs to go, but it gets scaled again based off of like how big your batch size is to compare to how big you want, like to how big your actual data set is, because you don't want it to learn everything on the first 5 epochs when you have 200,000 epochs to go. Does that make sense?
Yeah.
Okay. Anything else? Any other questions? Yes.
Does the learning rate change as you go through?
Yeah, you can change the learning rate as you go through. That's actually one of the methods that a lot of people use, and there's other methods. You can increase batch size as you go if you want to. But that is one of the better known methods for finding like extreme local minima on like certain things like transformers and stuff like that, where they change the learning rate over sort of like over time to change less and less the more like far down they go. Yes.
So the epochs are like these peaks in like the example?
Yeah, think of each epoch as its own data, like its own little mini data set, where each epoch has its own loss. So like the result of each epoch has its own loss, and then each epoch is different, but the sum of the whole, where you like find where the inputs need to go on an average for each epoch, then you found like a function that sort of represents the entirety of your data set. Does that make sense? So like each epoch has its own local minima, but you're trying to find like the average of local minimas over all the epochs. Does that make sense? Okay. All right. Is anybody confused?
So what exactly does the epoch represent?
So an epoch is just like a set of data. It's up in. It's just like a set of data that you want to use to train the actual model. So like it's like you don't do it all at the same time, or else you're going to run out of memory, and you just kind of iterate through and find like new local minimas for each epoch. So now that we're here, the whole picture is that you can have all these interconnected layers where they have all these different types of relationships, and you can find like all these different functions that fit. Like one of these layers could be linear, one of these layers could be logarithmic, one of these layers could be like arctan, for example. So a lot of times the actual layers in the network aren't the same functions being fit. So here's an example, I think it's on this one, of a multi-layer neural network fitting something. I'm actually going to put this as 2x speed. So you see the weights and the weight here being changed and the bias being changed as well, and how it can kind of fit. So this is a ReLU function. How it can fit these functions to make certain graphs. So here we're trying to fit a sine function. I'll just let this play. So you guys kind of get the point. I'll skip through a little bit. Basic idea is you can basically fit any function you want with these because they're multi-dimensional. Does that make sense? It's an approximation, but the approximation can be extremely good. Yes?
The red lines are being used to depict the sine graph. They don't have to be linear, right?
Yes, so the red lines depict this network, and the green line is what the sine graph is.
Yeah.
Yes. Do you have a question?
Well, I'll just ask.
Okay.
How do you decide like what final function you want to represent? Like why did they choose a sine instead of that?
So you can choose a sine one. That was just to represent like if you have enough things, you can fit pretty much any function you want. Like fitting a sine function with a bunch of linear functions doesn't seem like optimal, but if you think about it, like that just shows how versatile like a neural networks can be, where you can basically choose any function, and it can fit like sort of other functions. All right. So next, let's go on. Oh, yes.
Yeah, a follow-up question. So if you're trying to do something like classify data, would you instead have a function that like goes up in steps? Like if one output is like 1 and one is 2 or something like that?
So a lot of times when you try and classify data, you're giving each class its own output, where you have an output between 0 and 1, and it gives you a confidence. Yeah, that's called a softmax, typically, where where it tries to find like the probability that it's going to be that class, where it's like it's between 0 and 1 for like apple, and then it's between 0 and 1 for pear. Does that make sense? Okay. Yes.
So back propagation is like, is it at like starting with the result and then trying to figure out how to model that, or?
Yeah, it's starting with the result. It's basically, it's the actual minus the predicted. It's the loss, and you're basically trying to find the derivative of loss at that point for every different input. And if you guys have heard of a Jacobian, if you have, God bless your soul, it's basically if it finds a Jacobian and then changes it sort of one by one every time it goes through the network. I'm sure Ian knows what I'm talking about. But yeah, so now we're going to go on to applications of neural networks. I think Ian, you're first.
All right, guys. So the application I want to talk about is something from Telecom. What is this? I don't even know what this is.
All right, press down to go to the next slide. But
I won't need one. So basically, guys, I want to show you guys an example from like a telecom application. So in this sense, this is something that was happening at one of my internships I did, but basically, or at the internship I did, I should say. But basically, your CMTS is this thing where all of your routers and your modems, the cable head ends converge, right? And so this is your cable modem termination system. And inside of these things, you have particular channels that are running certain internet feeds and whatnot, right? So one of the applications that you can do is you can get back these error ratios through these frequency bands that show you how much loss you're getting in particular areas, right? And so when you read back a certain channel, let's say you have interference with cell signals in a particular frequency, you might see fall off on one end of that. So a way that you can use this kind of machine learning and neural network functionality is basically to classify these things. So this is actually like a real world use case that is pretty good at like optimizing your internet for when you're having outages, right? And so it basically says, if we're experiencing loss, we're gonna modulate that region so that we can fit more data in. And so basically like, you can classify several shapes, say like this, where you experience a drop off on the end. There are like 13 to 15 other shapes that you can classify and identify as like, well, these are things that commonly happen because of like signal error ratios. And from there, you could take something more complex like this and try to start mapping and classifying sections of it. And so using this, essentially like a closed loop automation system can say, well, what are we classifying and how bad is it, right? You're like, okay, well, we're experiencing a drop off, and it's not that bad because it's dropping off a little bit, so people in this frequency range might be losing some data, right? But like, if you see something like this, you're noticing like, oh, I'm having multiple losses. Like this is fitting in a range that's really, really bad for us. And so without anybody ever having to look at this, your machine learning model can go through, classify like, okay, we're gonna have a multiple drop model, or I don't know exactly what this model is actually called, but whatever this model would be called, it's bad looking, as you can see. And so basically this closed system can go through and identify these risks, and the CMTS that it gets it back from, right, this cable modem termination system can identify where this is happening, right? So like an operator can go out in the field and say like, I need to go reset this system now, because your machine learning model told you like, this is the worst case happening at the moment, right? And so basically it gives like businesses a real business value to assess like, what should we address first, right? So I figured this was an interesting use case because it's something kind of like, you don't see that often. Like it's hard to find, but it's something like that improves your everyday life without you knowing it, you know? So I wanted to show you guys that.
Thanks, Ian.
Yeah.
It was awesome. All right, next up we got Monsi, telling us about translation.
Hi everyone, I chose an example where we probably have used it every day, or we know people have used it. Google Translate's a big one. I know about 500 million people rely on this service. And this service uses recurrent neural networks, a specific type we'll talk about, and also uses an encoder-decoder model, which we'll see in the next slide. So basically, for when you're translating from one language to the other, you need to look at not just the word and like sequentially where it goes, but you also need to look at the word before and after and look at semantics and grammar and whatnot. So you want to use a biconditional recurrent neural network to look at not only just that one word, but it looks at the word before and after to help construct a proper, your desired output in that language. And in that first image, you can see how these RNNs do work. They take your input, which is your sentence or whatever in that language, and then translate it to a vector of numbers or weights. And then that converts to another vector, and then that final weights and like numbers is then translated to your final desired output. And with the biconditional neural network, you can put together two regular neural networks, which are chained, but they go in the opposite direction to give you your final output. And then here you can see how the encoder and decoder model does work. And yeah, I think it's and you can look at the week 6 from spring semester to look more about just recurrent neural networks and find them more in detail.
Yeah, the week 6 of last semester I talked about financial analysis, but the general idea of recurrent neural networks is gone over in that lecture. All right, Gabe.
Can you play the video?
Oh yeah,
And I think you can full screen as well.
I can.
Is that not
Oh man.
So,
It's as loud as it can on.
If that's as loud as it gets,
Python module and command line interface for easy facial recognition. And so the demo here
Sorry.
is AI, which is in facial recognition. So this GitHub repo shows a Python module and command line interface for easy facial recognition. And so the demo here shows the network learning the faces of Barack Obama and Joe Biden. So we'll be trying to find the
Oh man.
faces from this image, which is unlabeled as of now, and in this doc, here this is where we actually trained the network. Here we trained it to recognize Barack Obama and Joe Biden using these two images. Okay. And now that it's learned the encoding for these two images, we can run it. And there you go. It creates a bounding box showing that it recognizes which one is Barack Obama and which one is Joe Biden.
yeah, so that's just a small facial recognition demo using a GitHub repo that I found. But the use cases for facial recognition and facial detection are like very broad. There's of course crime prevention and surveillance. There's identity management with biometrics. There's also emotion recognition and healthcare, especially for example for mental health or for pain recognition in a hospital. You can use these neural network techniques to be able to help people in all of these different ways. So I want to talk about the different types of algorithms that are possible for facial recognition, because the main crux of facial recognition is getting the patterns you see in a face and somehow getting the computer to understand that. And there's two I'll talk about, where there's the convolutional neural network, and there's actually another one that's not neural network based.
Here, hold on. I'm gonna refresh. Oh, because it'll be all weird.
Sounds good.
Right here. Is this what
Yeah.
you want?
So a convolutional neural network, if you guys take a look at the GIF on the bottom left. Yeah, your guys left. It basically goes through an image, which is a list of numbers, because pixel values, and it aggregates the data by having this sort of sliding window method. And in this way, it captures features in the images. And this is known as convolution, like this sort of operation. And the cool thing about the CNNs is that different architectures can use multiple different CNNs to achieve different tasks. For example, you can have a CNN to extract specific structural features, but then you can have another CNN working in parallel to get texture features for the facial recognition. And then you can combine those results and put them into a classifier in order to be able to recognize a specific person. And so the image on the right shows how this CNN sort of works. By going through these specific bits of the image, it's able to capture data on what might be an important feature. And as you move through the convolution layers, it gets more and more data. And so by combining all of this, it's able to achieve this pretty cool result. And that's one use of the neural networks, but I wanted to also point out that AI and ML is not just about neural networks, because this algorithm does the same thing, where it splits an image, or by the same thing I mean it does facial recognition, but it does it in a completely different way. It splits the image into 8 pixel by 8 pixel cells or blocks, and it calculates gradients in each block, because what's really important in image classification and stuff like object detection is, for example, something like edge detection. So as you can see in the histogram-oriented gradients picture, the gradients are more pronounced, as in it's more white, when there's like more contrast. And so by using that like mathematical fact, they're able to create this system that creates description vectors based on these gradients. And by using these description vectors and putting it through a classifier, they can get very good results in terms of facial recognition. And I pointed this out because when I was looking through the code of the Python module I was mentioning, they actually have both of these different implementations. So yeah, I just wanted to point that out.
Oh, nice. All right, thank you, Gabe. Thank you, Monsi. Thank you, Ian. Thank you, guys. So this is my example that I made. If you guys want, you can go to this link. This is an example that I put together for classifying numbers, like handwriting numbers. For example, like if I wanted to classify 3, it would say that the probability of that being 3 would be 3. So that's just like an example of what I did. So let me open up here. Let me get here. So if I go, oh wait, I can't show that on here, can I? Hold on. Can I show my screen on here? I'll show my screen on this Zoom. I'm gonna go like this. Sorry guys. All right, here it is. Reconnect. So this is how we ran, oh, you guys can see it. Okay, sweet. So this is how we ran this is how we wrote the actual code. To input the data, we only needed 1 line. That's kind of why I use this data set. But here we defined the number of classes to be 10 because there's 0 through 9. And then the input shape of the size of this data set, MNIST, is 28 by 28 squares. And then 1 because it's black and white. If you had colored images, it would be 3 for red, green, and blue. So essentially, you load this data in, and then you convert them into floats, and then divide by 255 because it's between 0 and 255 for each value, and then you normalize it. So it goes between 0 and 1. That's what this does. And then you essentially expand the DIMs. You expand them, so you basically add another dimension. And then, yeah, I just output the shape so you can see that there's 60,000 samples. And we split it up into 60,000 trained, 10,000 test samples. So the model itself is a convolutional model, which we actually talk about in week 2 of last semester. And these basically, so I'm going to go up here. So we have this convolutional model, Com2D, that goes through the first one, and it creates 32 extra dimensions where each dimension is the actual first image going through the filter. So there's 32 different filters that they're trying to train, and then it creates a new dimension for each filter. Does that make sense? And then it does that again. So it does a max pooling 2D, where it takes a size of 2, and then it gets the max number. So like the number that's max in that 2 by 2 matrix throughout that entire image. And then we do that again. We go through and we have a convolution that creates 64 different filters, and then it does another max pooling with a 2 by 2 matrix. And then this flatten just takes the 2D array and makes it into a 1D array, so it's able to go through the network, and then we drop out. This dropout is good for training, especially for stuff where it's in a convolutional neural network, so certain pixels aren't weighted too heavily. Because what'll happen is if you have say it sees the same picture 8 times, or some pictures have the color green in this spot and it's always green when it's this class, we don't want it to become dependent on that certain pixel. Does that make sense? Awesome. And then this last dense layer is the actual regression layer, where it takes these 1,600 neurons that come from that flattened a 2D array, and it outputs 10 different outputs, 0 through 9. So then we set our batch size to 128, so it's running the loss function on 128 of these sample images randomly, and then it does it 15 times. So I guess I can run it through. It doesn't take too long to run. I wonder what it looks like on here. And then we run it like that. Did that go? Yeah, that went. And then we compile it, and then we fit it. So it shouldn't take too long to fit. Let's see if it's going to go fast or not. I think this says GPU. Come on. Yeah. So it just goes through this 15 times. As you can see, the loss is going down progressively. It's a good sign that your model is good. So the loss is the actual minus the predicted. That's what's being calculated here. And then the accuracy is what percentage it gets right. That's pretty much all accuracy is. But yeah, and then here, by the end, you can go here, and you can say that on our test data set on stuff it's never seen before, it got 99% of them correct, which is pretty damn good. And then you can go in and you can save the model into this H5, and you can download it. And then now you have a machine learning model that can predict the actual thing itself. And that's when we're in this demo here. Sorry if I broke your eyes right there. Where you can go in here and make it so somebody can draw an image, and then it scales that image to a 28 by 28 image, so you can see the scaled, resized image here, what it actually looks like to the model. And then it outputs its prediction of what probability it is for each different letter. So if anybody wants to try it, go for it. But that's basically it. Do you guys have any questions about the actual training of the model. Yes.
What did you mean when you said that it went through like 32 and 64 filters on your chain?
So like what Gabe had in the thing before, those filters, and I on week 2 of last semester I talked about convolutions in a lot more depth, but each filter. So do you see in this GIF the weights that is being sort of multiplied by? Those weights are solved for using backpropagation. So like those weights are like optimized for your certain data set. So what happens is then this convolution creates these sort of filters that are optimized specifically for your data set. And then there's 32 of them. So it trains 32 3x3 filters that all like find the most amount of entropy within your system.
Okay, so are all those 32 are all like uniquely made and then compared?
Yeah, so all 32 of those are like made using backpropagation, and then what happens once it's done like a backpropagation to find like the like optimal weights for say the first filter, if it goes through the second training loss, it'll only change it like a little bit based off of like what features it was correct on to sort of outline versus not outline. Does that make sense?
So is each like filter like iterative on the last?
Yes, every filter is dynamic. So you don't. There are models like of VGG16 where the filters are predefined, where like there's a pre-processing step and they predefine the filters. Does that make sense?
Yeah.
Awesome. Any other questions? Nice. Okay. I mean, we're done early. So, I mean, if anybody wants to try it out, go for it. There should be a link in the description of what it looks like, but I think that's it for today. Unless you guys have anything else to say. Yes.
Just something a bit different. I just like have a bunch of cookies that I brought from something else. I don't know if you want to offer it here.
Oh, nice. Yeah. That would be awesome. Thank you. Yeah, see, come in person next time we get cookies.
No, this is not guaranteed. I just had these from something else today, but yeah, these cookies, hopefully no one's losing.
Awesome. Thank you.
Sure.
That's great. I think I'm going to stop the stream though. So